you.
Is Jared connecting with us today?
He is. He's trying to get logged in.
All right.
Well, he's doing that because he can hear me too. There was some confusion about the omega equaling the change in theta over the change in time using that equation compared to using the theta equals the 1/2 alpha t squared.
Okay.
I can explain why it was different. Why I can't explain that. Because when I was doing, this was on problem number 4, and when I was trying to use the omega equals theta over t, I was getting twice the angle that I should, and I don't know how I ended up realizing I needed to do the 1/2 alpha t squared, but
Well,
that's how they were related. So can you
it
explain?
really depends on if there's acceleration or not. If you have acceleration, if there is an alpha, you can't use you can't use the omega equals delta theta over delta t, because that's only if there's no acceleration.
Okay, gotcha. If
you
there's
do
a
have
constant,
acceleration, then when you have acceleration, you have to use one of the kinematic equations, and the alpha 1/2 alpha t squared is a kinematic equation.
okay. So you could only use the other if it was just a constant velocity.
That's correct.
Okay.
So yeah, it's actually very much the same as the linear motion, where there are certain equations like the definition for velocity and the distance that you travel at constant velocity or an average velocity. Those equations only work if you have the average velocity or the velocity remains constant. And then all of the rest of the kinematic equations that have a in them or alpha in them, those ones you have to use when you have a constant acceleration. So
Gotcha.
you just kind of have to differentiate between the two.
I know, there's just so much to remember.
Yes, indeed. Okay. Let's see here. All right. So I believe that we have finished chapter 10. And now we're just going to answer questions. I want to answer questions primarily on chapter 10 to start off. But then if we want to go on to something else from previous chapters to get ready for the exam, then we can. See if I can find my, there we go. Let's see here. All right, so what kind of questions do we have from chapter 10 homework? Do we have any others?
Number 5, I think, the one with the box.
Number what?
5, I think.
This one here?
Yeah.
Okay. So in this problem, we're kind of entering into the real world a little bit here. In previous chapters, we would have maybe approached this problem from the idea of just straight out forces, where you have the weight of the object pulling down here, right? And then this thing would just accelerate because of the weight of the object. However, the problem here is that the weight, the force from gravity pulling down on this mass has to do two things. It has to accelerate this mass, but it also has to angularly accelerate this pulley, because this pulley has mass and it has a radius, and so it takes energy to get that thing rotating. So part of this force has to do the rotation there. So this mass is not going to accelerate like it would have before, because it has to get this thing rotating as well. We're going to split the force up between rotating this and accelerating the mass down here. So how are we going to deal with that? Well, I think the best way to do it is actually to look just at this part right here. So now we're going to move our force that's down here to up here. It's the same force because gravity is still pulling on this mass. So this force right here is still equal to what we would expect it to be equal. It's the weight of the box, which equals the big M. That looks like a Z, not an equals. Equals the big M mass of the box times gravity. But this is also a torque because it is pulling on this circle at the edge of this circle at a distance r away from the center of the circle. And so it's related to a torque. And so this is equal to a torque, which equals the force, which is the m times g, times the distance to the center of rotation. So it's r times m times g. The sine of theta gives us sine of 90, which is just 1. So there's the torque. So we have a weight pulling on it. That weight is causing a torque, and this is that torque. But also, one more thing, remember that torque is equal to I times alpha, or the moment of inertia of the pulley times the angular acceleration of the pulley, right? Now, this is something we can work with. We know R, we know M, we know G, and we can calculate I for a rotating disk. This is what it looks like. R times M times G, and the moment of inertia of a rotating disk is 1/2 times the mass of the disk. Well, the mass of the disk is little m, not big M. So it's the mass of the disk times the radius squared. And now we have an equation that we can solve for alpha. We know everything in this equation except for alpha. And that goes right here. Now, since the rope is coming off of the disk in a line, then the acceleration of the rope is going to equal r times alpha, the acceleration of the disk. They're related to each other because the rope is coming off of the disk. It's like a wheel rolling on the ground. So that takes care of your first two. Then you can use a kinematic equation with acceleration and calculate the time, because you know the initial velocity. You know the initial angular velocity is 0. You know the acceleration alpha. And let's see, what else do you know? I'm not sure what else you know. Oh, you know the distance. Here we go. So you know the distance that it travels. That's kind of like X or Y or something like that. If you wanted to call this Y, the distance that the rope comes out in the Y direction, that's going to also be equal to R times theta. So you know you can calculate theta. And with these three things, you know your final theta, you know your initial theta equals 0. Start at 0 and go off to some angle theta. Then you can use a kinematic equation to find time here. And once you found, and right here, when you use this distance in y to calculate theta, you can put that answer down here in that section, and so on and so forth. So all of these problems kind of follow the same type of pattern where you're looking at a problem and you're saying, well, I'm not sure if I know how to do this, but really the key is to look at where the rotation is and try to see how that's connected to the linear motion. In this case, the rotation of the pulley is connected to the linear motion of the rope. The linear motion of the rope is caused by the linear force of the weight on the end of the rope. That weight translates to a torque. That's rotational. That's the rotational Newton's second law right there. And then once you use torque to find alpha, then you have your angular acceleration, and you can start using kinematic equations. I'm going to let you figure out what equation to use here, but it's just one of the rotational kinematic equations that has time in it. Does that help?
Yeah, it does.
Good. So always kind of look for where the linear connects to the rotational, you know, because oftentimes it's a linear force that's causing a rotational thing, so that you can turn that linear force into a torque and get an angular acceleration using a moment of inertia or some kind, different shapes. And then once you've got that angular acceleration, you can start looking at kinematic equations to see if you can solve for other things, and so on and so forth. What else? Anybody else have questions? No more questions? We're all done? Well, if we're done and there are no more questions, then I guess we can answer questions from previous chapters, or we can be done for today and we can answer questions from previous chapters tomorrow. Depends on what you want to do. Does anybody have any questions from previous chapters that they've been looking at to get ready for the test at all?
If we ask questions tomorrow, I can run back through. I haven't run through any right yet.
I'm not sure what you said there.
If we ask questions about previous chapters tomorrow, I can run through and get some.
Yeah, that's fine. Remember that this next exam is chapters, I think, 6 through 10, right? The 6 through 10 or 7 through 10? I don't remember. Let's go take a look. 6 through 10, it looks like. Exam for chapters 6 through 10. Looks like there are 14 questions on it. And if we go back to chapter 6, we can just kind of get a quick overview. We're essentially doing, we're doing two different things in this next exam. We're doing circular motion, and then we're doing also energy. So we start off with a basic introduction to circular motion, which I actually would have preferred they either did later or did, I don't know, whatever. But they do a basic introduction to it where they introduce us to centripetal force, centripetal acceleration. They also talk about rotational angle and angular velocity. And then they go into fictitious forces like the centrifugal force, the Coriolis force. Then they talk about Newton's universal law of gravitation. We did some stuff with satellites and Kepler's law of planets and moons and satellites and things like that. Then we went on to energy and momentum. So we spent cut two chapters talking about energy and momentum in linear form. So energy being, of course, the the ability to cause things to accelerate, to cause things to bend, to cause things to break. The energy is related to forces doing things in the real world. And we talked about different kinds of energy. We talked about work, which is the force moving something some distance. We talked about kinetic energy, which is the energy that is actually embodied in movement. So movement itself has energy associated with it. And we talked about the fact that work can put kinetic energy into a system by moving it. Gravitational potential energy is this idea that the closer you are to something gravitationally, the closer you are to some kind of mass, you have more pull on you. The further away you are, you have less pull on you. But the further you are, the more potential you have to get pulled. And the closer you are, the less potential you have to get pulled because you've already been pulled pretty close. So that potential is almost like the opposite of the gravitational pull. It tells you how much you could be pulled and you haven't been pulled yet. When you have more gravitational potential energy, you're usually farther away, or in the case of being on Earth, you're higher up away from the surface of the Earth, right? And less potential energy, you're closer. Then we talked about conservative forces and potential energy, where conservative forces are defined by forces that can cause movement that is not lost by friction or heat or breaking or bending or sound. Excuse me. And then non-conservative forces were things like, friction that caused heat, and heat kind of wanders out of the system, and sound, which kind of wanders out of the system, and breaking of things, which kind of wanders away. These kinds of energy are not conservative because they don't keep the energy in the system. The energy leaves the system in some way and just dissipates into the universe. Conservation of energy being this idea that if you have a closed system with no non-conservative forces, you can actually measure the amount of energy before and after, and it should be the same. Power, then we talked about, where power is the amount of energy being used every second. So it's kind of like the velocity of energy use or something like this you can think of. Then work energy and power in humans, and world energy use, more about how we're using energy in the world. This one's kind of interesting because it talks about essentially conservation of energy and the human energy cycle, eating, exercising, whatever else. And this one is mostly kind of just where the energy goes that we create from others. We take one source and we create different kinds of energy out of it. So take a lump of coal, which has a lot of chemical potential energy in it, and we burn it, and we create heat potential. We create heat energy, and we create light energy, and we create from that heat energy, we heat up water and create steam, which creates kinetic energy in a turbine. And all along this process, we're losing energy and all those other things. We talked about where that energy goes after we convert it into a useful type of energy, and the efficiency thereof. Chapter 8, linear momentum and collisions, where momentum is also related to force, but it's not so much about the force that causes things to move a distance, but it's a force that is applied over a certain amount of time to an object. And conservation of momentum we talked about, and then we started talking about collisions, different kinds of collisions. Elastic, where momentum and kinetic energy are conserved. Inelastic collisions, where only momentum is conserved. Two-dimensional collisions, rocket propulsion, so on. And then chapter 9, we talked about statics and torque, where statics talks about the idea of an object being completely, all the forces add to zero, so it's completely without acceleration. It could be stopped, or it could be moving at a constant velocity, but all the forces add to zero. But not only that, but all the rotational forces, so all the torques add to zero as well, so that it doesn't accelerate in some kind of rotational way. And we talked about stability, but then we went on and moved on to machines and forces and torques in muscles and things like that. So we were talking about torques, even and in this section we even talked about I guess we didn't actually, never mind. Not till chapter 10. And then of course, chapter 10, we went on to discover things like the moment of inertia, which helps us to connect torque to angular acceleration, and also helps us to connect angular momentum to angular velocity. And we talked about all kinds of things when it went to when we were talking about rotation and linear motion at the same time, kinematics of rotation, relationship between rotational and linear kinematics, all these different things we've been learning about. So that is just a quick overview of everything we've learned in chapters 6 through 10, and those will be the things that are on the exam. And then we are going to be done. You'll take that exam on Wednesday and Thursday. I will split it into 2 separate exams. And you'll take it on Wednesday and Thursday, and then we will be done until we come back in January. Well, what day do you guys come back in January, Julie?
We come back, I think, on the 7th, maybe, or the 6th. I don't think the kids come back till the 7th. I
Okay.
think we come back the 6th.
Do you want to start right away that week, or would you like to start the next week? We don't technically start till the next week, but we can start early. Doesn't matter.
Yeah. We can start the next week. That's okay. We won't, because that will be, we would only have one day anyway that week. So.
Okay. All right.
All right.
Well, let's go ahead and do that. We'll go ahead and start the week after that on Monday.
Okay.
Tomorrow, let's have everybody just kind of review their homework and review the chapters and see if they have any questions to talk about tomorrow. And then tomorrow we'll answer questions from all the chapters 6 through 10. And then I'll have the test ready for you guys.
Sounds good.
All right. Have a good afternoon and evening.
Thanks. You too.
See you later.